This is the debrief on the limits test. This is the test you had yesterday on the 24th. Problems 1 through 11 deal with functional values and limiting values. Let's look at the functional values first. These are problems 1 and 3 and 5 and 10. These are asking where's the function defined at various x values. Okay, number 1, g of -3. Here's -3 on the x-axis. We see a dot here, and that's at 1. So g of -3 is equal to 1. Remember, functional values are defined as y values. Second one, g of 1. We find 1 on the x. We're looking for the appropriate y value. It's up here, and this is at 3, so g of 1 is defined to be 3. Okay, g of 5. Here's 5 on the x value. Here's the dot, and that's defined to be -1. And g of -6, we go to -6, which is right here. We're looking for the dot. There is no dot. Notice that's a hole, not a dot. So g of 6 is, we should probably scratch the equal sign and write is undefined. Notice that functions are defined or undefined. If we get to limits, we'll do in just a little bit, limits exist or do not exist. And if we had to solve an equation, which we were not asked to do for this problem, equations have solutions or have no solutions. Okay, so there's the functional definition questions. Now let's look at the limiting questions. For the limiting questions, we don't care if there's a point. What happens at the particular x value is of no concern. We only care what happens when x gets close to the particular x value. So here we are at -3, and the question is what's happening to the function. Now remember, what happens at -3 is irrelevant. All we care about is what happens when we get close to -3. So let me sort of blank that information away. Well, as we get close to -3 coming in from the left side, how about a larger picture? If we get close to -3 from the left side, we're coming in like this. The function is rising, 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 and getting close to 1. Unfortunately, when we approach -3 from the right side, the function is down here, and that's at -2. Now again, recall, it doesn't matter what happens at -3. All we care about is what happens when x gets close to -3. The function is not getting close to 1 value, but rather it's approaching from the left, it's approaching this value, and from the right, it's approaching this value down here at -2. So go back to the problem. We have to say the limit does not exist. Does not exist. Okay? Let's see what happens when x gets close to 1. This is problem number 4. So again, maybe a large picture would be useful. X is getting close to 1. What is the function doing? Okay, so here's 1 on the x-axis. We can block out this information. We don't care what happens at 1. We only care what happens as we get close to 1. And certainly as we get close to 1, coming in from the right and from the left, the function is approaching this particular value, which is -2. The fact that there's a hole there is irrelevant. We don't care that there's a hole. All we care about is as we get close to 1 from the right, the function is dropping down to -2. And as we get close to 1 from the left, the function is going to -2. Okay, this is a one-sided limit here. This is asking what happens when x approaches 5 from the left side. Here's our picture again. X is getting close to 5 from the left. Here's 5. Whoops, here's 5. And we're getting close to 5 from the left. So as we come in this way, the graph is obviously rising, and it's getting up to this level up here. The fact that there's a hole is irrelevant. I don't care what happens at 5. I only care what happens when I get close to 5. So the limiting value is, in fact, 2. Okay. How about when x gets close to 5 from the left? Sorry. One of these was from the left and one of these was from the right. Hang on a sec. Let me see if I can pull up the original. Obviously, when I copied this, it didn't come out very clear. number 6 was from the right, and number 7 was from the left. Okay, so let's see. Number 6 was from the right, and number 7 was from the left. So this is the 2 over here. This is coming in from the left. Coming in from the right, okay, now we're coming in this way, and the graph is rising to -1. Okay, so sorry about that. Now, notice number 8 is asking what happens when x gets close to 5. We have to take into account both coming in from the left and coming in from the right. This limit does not exist. The function does not go to one value. Limits have to be one particular number. Obviously, the left limit and the right limit are different values, so that limit does not exist. Okay, let's see what happens as x goes to positive infinity. This says x is getting really large. So think of 5, 10, 15, 20, 25, 30. The way the graph is indicated, as x goes out that way, the graph stays at this level, and that is at -2. So the end behavior is -2. Whoops, -2. And the last question, what happens when we approach -6 from the right? Well, again, pretty clear, I think. We're approaching -6 from the right. The graph is heading down to this particular level right here. So going down to -2. Don't care that there's a hole there. That has nothing to do with the limit. All we care is what happens when x gets close to -6. The graph gets close to -2. Okay, so there's your first 11 questions worked out. Okay, the next batch of questions, well, we're talking about the definition of a continuity at a point. So we just recall, I remember this was open notes. You should have this written down. If f of x is continuous, f of x is continuous at x is equal to c, then 3 things had to be true. The function needed to be defined at c. F of c is defined. The second thing had to be the limit was existing. So the limit when x gets close to c of the function had to exist. And the third thing is the limiting value had to be the defined value. So the limiting value when x got close to c had to be the same as the defined value. Okay, so that was in your notes. That's the definition of continuity at a point. This particular question asks what happens if x happens to be 10. So you just write the exact same things. F of 10 is defined. The limit when x gets close to 10 of f of x exists. And lastly, the limiting value as x gets close to 10 of the function f of x is in fact f of 10. So exactly the same as this, except you write 10 instead of c. Okay, another graphical picture. The first thing they talk about are discontinuities. Let's see, in our graph we had an arrow here and an arrow there and an arrow there. And the first task is how many discontinuities? Well, think about coming in from the left, I suppose. As you're going along the x-axis, certainly this graph is defined until we get to -8. There's a hole, so that is a discontinuity. We had to pick up our pen when we got to there. Also at -3, there's a discontinuity. We had to pick up our pen. There was a jump. And then lastly at 2, well, I guess not lastly at 2, there's a discontinuity here. We had to pick up our pen, and it jumped, and it did all sorts of weird stuff. And then at 4, we had to pick up our pen again. Okay, so there's 4 x values where we have discontinuities. Okay, the x values, discontinuous, discontinuous at x is equal to -8, -3, 2, and 4. Those are the places where the graph is discontinuous, 4 of them. Now, of each x of those x values, there's a term that applies to this discontinuities. The removable discontinuity is this. That's where the hole is. Notice the limit exists, but it does not equal the functional value. Infinite discontinuity was at 4. That's where we had the vertical asymptote. Whenever you have a vertical asymptote, that's an infinite discontinuity. jump or step discontinuities are, obviously there's more than one answer here, so there's a jump at -3 and at x is equal to 2. So you have to have both of those. The last question was what happens as x travels off to the left. The function is obviously rising, 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 so you could write positive infinity, or if you want, you could write does not exist. Okay, so that was another graphical problem. Second page. Oops. Second page. Use your calculator to find the indicated limits. It also notes in this problem that you can actually do 19 and 20 without a calculator. So even if our calculator was not working, we still might be able to get these answers. But let's go ahead and try these with the calculator. The first one deals with the expression -2 sine of 3x divided by the quantity 5x squared minus 4x. This is not a derivative, so there is no shortcut way of doing this, I suppose. We're simply asked to put in values close to 0. So 0.001, that's pretty close to 0. I'll put that into the function. I can try on the other side of 0. So -0.001, both of these are close to 0, and it appears the functional value is close to 1.5. Okay, number 19. 19, again, sort of the same drill. We'll put in the cosine of x squared minus 1, and we're dividing by the quantity 3 times 2 raised to the x power minus 1. Okay, and we're asked to put in values close to 1. So vars, y vars, function of value close to 1 might be 1.001. Oops, 1.001. That's pretty close to 1. And if we try on the other side, another value close to 1 might be 0.999. That's pretty close to 1. And we see both of these are getting close to 1/5 or 0.2. Okay, so 0.2 or 1/5 would be the answer there. And the last one, again, on our calculator, we're putting in this expression here, where we have the quantity 3 minus 2x. Oops. Let's see. Clear. Okay, the quantity 3 minus 2x. And we're dividing that by the quantity 5x plus 4. Okay, I lost a set of parentheses here. There. Okay, and we're asked to put in big numbers. So what does a big number mean? Well, let's sort of do it in orders of magnitude. If we put in 10, we get that. If we put in 100, we get that. If we put in 1,000, we get that. Let's sort of put in 10,000 and see what happens. Okay, so obviously as x is getting larger and larger and larger, this appears to be getting close to -0.4, and that is the answer, -0.4, or if you want, -2/5. This particular bonus question does say you can actually do 19 and 20 without your calculator. For all limits, you should try direct substitution. So for this one, if you just let x is equal to 1, we get the cosine of 1 squared minus 1 divided by 3 times 2 to the 1 minus 1, which is the cosine of 0 divided by 5, which is 1/5. Okay, so we could do that one without a calculator. And if you just sort of explained how that would happen, you'd get a couple of bonus points. Likewise, we can do this one without a calculator. Note that this is a rational function. You can think about graphing it. If we were to graph that function using Vukovic, we would find there'd be a 0. 3 minus 2x is equal to 0. 2x is 3. There's a 0 at 3/2. There's a pole. 5x plus 4 is 0. 5x is negative 4. There's a pole at negative 4/5. Negative 4/5. X is equal to. And for end behavior, recall we would look at the powers, right? So this is x to the first, and this is x to the first. So for end behavior, we're dealing with the ratio of the leading coefficients. So it's negative 2 over 5. There'd be a horizontal asymptote here at y is negative 2/5. The graph would look something like this if we were to actually graph this guy. We have this and we have this. Okay, so that's the graph of the function, and sure enough, as x gets big, the graph gets close to negative 2/5. Okay. I looked at 21 and 29 together. Both of these are problems that you should have in your notes. This definition is called f prime of c, and this definition is f prime of x. You just need to know those as definitions. F prime of c is a limit as x goes to c of x minus c, f of x minus f of c. This gives the slope of tangent line to graph y is f of x at the point x is equal to c. Okay, and f prime of x is a limit as h goes to 0, and you got f of x plus h, take away f of x, and this particular limit, this derivative, gives you the slope of the tangent line to graph of y is f of x at any point x that's in the domain. Okay, so yeah, you're just supposed to have those two things memorized. That was just write them down, all or none. Okay, evaluate each limit using algebra. Showing enough work to justify your answer using your calculator alone to arrive at the correct answer earns no credit. Limits are numbers. This number is equal to 27. This number is equal to 1/3. This number is equal to 6. And this number is equal to 3/4. Now, we can get the numbers on your calculator, but you get no credit for doing that. So now we have to do this algebraically. We do have to keep in mind that each of these is a number. So whenever we're working this problem and we have this equal sign, we have to think that thing is equal to 27. Let's do them individually. Okay, so the first thing you should do is realize that this is a number. So we can write this as a limit as x goes to 3. We're going to factor the difference of cubes, x minus 3, x squared plus 3x plus 9 all over x minus 3. Okay, so this limit, which is equal to 27, is the same as this limit, which is equal to 27. We can cancel these. And so now this is equal to this limit. Limit as x gets close to 3. We have x squared plus 3x plus 9. And now you can try direct substitution. So you put 3 in. So you get 3 squared plus 9, which is 27. This is 27. This is 27. This is 27. If you wrote this, that is not 27. So you would have lost half credit if you simply wrote equals this. This expression, if I were to go out in the hall and just ask someone, what does that equal? No one will say that equals 27. Okay? It's only the limiting value of this. It's the limiting value of this expression as x gets close to 3 that equals 27. Okay, so same idea here. This happens to be the fraction 1/3. It is a limit as x gets close to -1. We'll go ahead and factor the bottom. This is a sum of cubes, x plus 1. So we have x squared minus x plus 1. So this whole limit is going to be equal to 1/3. We cancel. Okay, and now we have this. Make sure you have the equal signs. Limit is x goes to -1. And we have 1 over x squared minus x plus 1. Direct substitution. So you get 1 over -1 squared minus -1 plus 1, which is 1 over 1 plus 1 plus 1. Okay, so sure enough, it's equal to 1/3. This is equal to 1/3. This is equal to 1/3. This entire thing is equal to 1/3. Equal signs are important. Connect equal things with equal signs. If you left off an equal sign, then you lost some credit. Okay, you can't simply write in mathematics, you can't write 2 plus 3, 5. You have to have the equal sign in between. Okay, so when you're connecting equal things, use equal signs. 24. This one you can do 2 ways. Probably the simpler of the 2 ways is simply to factor the numerator. And this is the limit as x goes to 9. I factor the numerator as root x plus 3 times root x minus 3. The denominator is still root x minus 3. I can cancel and substitute, put 9 in for root x, and we get root 9 plus 3, 3 plus 3, which is 6. This is 6, this is 6, this entire thing is 6. If you left off the limit expression, you lost some credit. And now the other option here is not to factor it, but to use the conjugate. So if we had the limit as x goes to 9, x minus 9, over root x minus 3, we can multiply this by the conjugate, root x plus 3, root x plus 3, and then realize that this limit, x goes to 9, I'm going to leave the x minus 9 up top and not multiply this out because I'm going to expect the x minus 9 to cancel. On the bottom, root x by root x is x. Notice the middle terms drop out as the difference of squares pattern. And so we have x minus 9. And sure enough, they cancel. Lastly, substitute. You're putting 9 into this expression, root x plus 3. And so once again, root 9 plus 3, which is 6. You don't have to write limit here. This is the number 6. Okay, so it's sort of sloppy to put the limit as x goes to 9 of root 9 plus 3. Okay, the last one was probably the simplest of the lot. Simply factor and cancel. So once again, limit x gets close to 2. The bottom is your difference of squares. The top factors very easily as x minus 2, x plus 1. Cancel, substitute, 2 plus 1 over 2 plus 2, 3/4. Okay. Problems 26, 27, 28 are dealing with average rate of change. This is simply a change in y, change in x. So change in y, change in x. It's just a slope, right? We know the x values. They're given as 2 and 5. By the way, you could also do this as 5 minus 2. Both of these are correct. But up top, we have to put in the y values. Let's see, if x is 2, y is 1/2. And if x is 5, y is 1/5. Okay, so we have 5/10 take away 2/10 is 3/10, and minus 3. So we have 3/10 times minus 1/3, which is minus 1/10. If you did it this way, by putting the 5 first, there's no problem with that. You'll get the same answer. Make sure you put the 1/5 first, and then the 1/2. So again, 2/10 take away 5/10 is negative 3/10, and this is 3. So negative 3/10 times 1/3, which is negative 1/10. Average rate of change. I suppose you could use your calculator on here. It didn't say you couldn't. It did say show the work. So I suspect if you showed that, and then just dump that into your calculator and wrote -1/10, I would have given you credit. The idea is you're subtracting 2 y's, subtracting 2 x's. Okay, 27, same function, but instead of going from 2 to 5, we're going to 2 to 2.1. So again, change in y, change in x, 2.1, take away 2, and now this is 1 over 2.1, which looks a little awkward, minus a half. Let's do this without a calculator. On the bottom, obviously, we have 1/10, right? 2.1 minus 2 is 1/10. And up top now, this is the reciprocal of what? Let's see, 21/10, right? 2.1 is 21/10, and this is 1/2. So let's clean this up a little bit. This is 10 over 21 minus 1/2 over 1/10, and we'll clean that up a little bit. So 10 over 21, take away a half, and multiply that by 10 over 1. So we get 100 over 21 minus 10 over 2. And I suppose I should probably clean that up a little bit more. Common denominator is 42. We have 200 over 42. Take away 210 over 42. The answer is -10 over 42, or -5 over 21. I had a number of people actually do this on their calculator, which is fine. The idea, of course, was to set up the difference quotient. If you grabbed your calculator and just let your calculator do the arithmetic, I would have been fine. So 1 divided by 2.1 minus a half, I know that's a half, divided by, and I can just write 0.1 there. Okay, so I would have gotten that, and if I turn that into a fraction, once again, -5 over 21 is the answer. It is an equal sign. There's no approximation here. If you gave me something close, for example, if you wrote down -0.38, that's wrong. Okay, so equals -0.38, -0.238. That's wrong. It does not equal that. It does equal -5 over 21. And if you're going to argue with me, I would just ask you to tell me what 5 divided by 21 is, and it doesn't equal -2.38. Okay, that's a good approximation, but it's not equal sign. So I would have marked that wrong. The last one talked about the instantaneous rate of change. Obviously, we don't have a tangent line here, or we don't have a secant line. We have a tangent line. This instantaneous rate of change, you know already that this is a limit. There's 2 ways of doing it. Limit x gets close to 2, x minus 2, 1 over x minus 1 over 2. Because this is f prime of c, remember we have that canned program in your calculator. If you just jumped into Math 8 and put in the 1 over x function with x as the variable and 2 as the value, you get the answer. Well, technically you don't get the right answer. The right answer is in fact -1/4, not -0.250000000625. The program approximates the rate of change. The answer is -1/4. If you wanted to get it exactly, you would have to do the limit, which again isn't terribly hard. This does work out to be -1/4. So let's see, limit x goes to 2. Common denominator here is 2x, so 2 minus x over 2x, and this is x minus 2. Let's go ahead and clean that up algebraically. Limit x goes to 2. We have 2 minus x over 2x times 1 over x minus 2. And again, you should recognize that these cancel, but they don't give you a 1. They give you a -1. So the limit now becomes this. X goes to 2 of -1 over 2x. Direct substitution, -1 over 4 is the answer. Okay, last page. This one, a lot of words, but it was on a worksheet, so not a lot of new stuff here. It says find the average rate of change. This is just a slope of a secant line. Velocity with respect to time, and the interval is 0 to 16. So all we're doing is we're finding the slope of this line, msec. And that's change in velocity, change in time. So 20 minus 0, those are the, this is obviously 0, 0, those are the velocities. And the times are 16 minus 0. This does say, don't forget the units. Okay, so velocity was for this problem in meters per second, and time was in seconds. So I guess we should include those over here, meters per second. And seconds, answer 20/16 meters per second squared, or if you want 10/8. 10/8, 5/4. Okay, so 5/4 meters per second squared. You actually got a point for the number, and you got a point for the units. If you had meters per second squared, you got half credit, even if you didn't have the right number. Many limits cannot be done algebraically. Use your calculator to find the value. They're quickies. All of these, again, note, are of this form where x is going towards a particular number. You have x minus the number on the bottom. You have a function, which happens to be the log function in each case. The log function minus f of the number. So for example, this one, x is going to 4. There's a 4. There's a log of 4. You might wonder about this one. Well, this does have the log of 1, but you know the log of 1 is 0, so it'd be sort of silly to write that. So because all of these are derivatives, we can do all of these quickly with Math 8. We have to put in the function and the point, and we're good to go. So for the first one, the function is the log function. The variable is x. The number is 1. We get 1. The second guy, we just have to change this to 2, and we get a half. Now notice that all of these are not quite exact. The inderiv program does approximate these things, but in fact, all of these will work out to be nice rational numbers. This one is 1/2. If we change again, we put a 3 in, we get a third. And if we put 4 in, we get a quarter. 4. Okay, so these are the limiting values. These are the rates of change. The last question asks you to look at this with sort of a analytical eye. Math is the science of patterns. Use the results above to find the pattern that gives the derived function for this special limit. We already know this is f prime of x. F prime of x, that was tested at the top of the page. F prime of x. And in fact, f of x is the natural log function. That's the one that we've been dealing with for this particular set of exercises. So we're asking what happens when x gets close to a number. And we have the natural log of x minus natural log of x minus the natural log of c. Well, it's pretty clear that this always works out to be 1 over c. What I was looking for this, and again, this may have been the hardest problem on the test. I wanted you to say 1 over x. I had a number of people say this, and I gave them credit for it. I had a number of people say 1 over h, which is not correct. Remember, h is going to 0. If h goes to 0, this expression would blow up to infinity. That's not what we want. We want 1 over x. 1 over x. And there was a few hints here. If correct, if f prime of x really is 1 over x, then f prime of e would be that number. F prime of pi would be the number up there, and F prime of 7 would be these numbers that were given in the hints. So this is just sort of a check on reality. And let's just double check. We'll get out of here, clear. 1 over e, 1 divided by e. Sure enough, we have the right approximation, or 1 divided by pi. 1 divided by pi, these are obviously irrational. 1 divided by 7 is rational, but it does have a repeating decimal, 142857, 142857, etc. Okay. Some people came to me after the test and said, well, I didn't realize that the ones above were derivatives and it took too long to do. Well, I'm not sure that would have been the case. If we go back to these and say, how can you do these without realizing they're math 8? Then you could do just like we did on the top of the second page, and you can put in the entire difference quotient, which is rather awkward, but we can do that. For example, here's d. Now we put in the natural log of x and subtract off the natural log of 4 and divide that by x minus 4, and whoops, parentheses here, divide that by x minus 4, got it, and then we would just put in numbers close to 4, so like 4.00001, parentheses here, function notation, Joe, that's pretty close to 4, and if we put in 3.99999, that's pretty close to 4, and both of these are approaching 1/4. So you could have done it that way. A little bit more tedious. The good news is once you've put it in, once you've put the difference quotient in, it's not hard to change. If we wanted to try problem part C, this would have to be a 3, this would have to be a 3, and then when we go to here, we would have to put in numbers close to 3. So like 2.9999, oops, 2.9999, that's close to 3. Or we could put in a number like 3.11111. That's close to 3. Okay, and once again, we get 1/3. Okay, so I hope that helps. Certainly study the return test. Figure out where you went wrong. If you want to retest, talk to Mr. Melson or myself, and retest will be available tomorrow, not today. Thank you very much.